Hello, this is Miles Jaffee recording the video for homework 3 for CS262. I'll just start with my interpreter file. Actually, I should start with my parser file to explain the changes I had to make to that parser. So the default parser, let me find it. The default parser only accepts math expressions with plus and minus. So I had to design, as well as get some Gemini help, just with filling out the logistics of doing PEMDAS on it and being inclusive of multiple expression or multiple operator statements. So the base level, the stuff with the highest precedence, is values that have their own value. So function calls, raw values, and parenthesized anything. Then the next level of precedence is exponents, then multiplication and division, and then math expression is defined as just getting plus and minus, and checking for the multiplication and division terms, which in turn checks for the exponent terms, which in turn checks for base units. I don't believe I changed anything else in the parser. So the interpreter, let's start with the math expression to get that out of the way, because that was one thing that I spent a lot of time on in this case. So when we see a math expression node in the AST that's outputted by the interpreter, we're going to look at the right side, or the left side and the right side, which, because of how the parser works, will always be a number value, or sorry, not a number value, but it will always have two children. So no need to fill out this part of the else branch, although I guess that should probably be unimplemented or unreachable. And then we just match the operator to what happens. Let's go back and look at this stuff. So the interpreter has both a stack and a hash map of functions. The hash map of functions works the same as each stack frame, except that it maps to a vector of nodes instead of just to one value. We have this helper function, which was created with AI help, although I had the basic idea for the functionality. And that turns a vector of U8s, which is what we get out of the name, function call, etc. in many instances of the nodes. So it takes that and turns it into a non-collection format, which is to say U64, a compilation together of the first 8 bytes of the vector, or if there's not 8 more bytes to look at, just padding it out. If there's more than 8 bytes, so more than 8 characters, it truncates it. This does restrict the space of the kinds of functions that, or variable names that you can use. But for a test program like this, where every variable is going to be only a few characters long, it's fine. This would obviously have to be a larger value, like a larger storage, maybe a string, or similar in a real world environment where you were having production variables potentially with long names. An interpreter is initialized with a stack, which has the basic frame on it, and a hash map of callable functions. And to execute a command, we look at this match statement. We execute anything other than a return statement and return a return statement. And then at the end, if we didn't have a return statement here, we return the most recently executed statement. And if there was nothing executed, it's just a Boolean that says true. That's the default value. We showed the math expression. The identifier tries to get the value of a vector of bytes that's passed to it. It currently can only get things from the most recent frame. Going back through the frames and getting previous items would be an interesting way to extend this program to the functionality that is specified. But I decided that was out of scope for this project, even though it is pretty basic functionality. And if it can't find the identifier name in the current frame, it gives an unidentified function error. When we're defining a variable, very similar, we are putting it into the last item on the last stack frame. And if there's some kind of error with the name of what's being defined, then we have a predefined error message for that in a predefined case. And this minimum U64 value is just 0, 0, 0, 0, 0. The ASCII byte 0 being a byte that is never found in normal plain text, so we'll never just accidentally run into it. Defining a function is similar to defining a variable, except we don't have a stack frame situation with functions, so it's just inserted into the function hash map. A function call is by far our most complicated arm of this big match statement. We get the name of the function that's being called, and we get or try to get the children of the function, which as you can see in these example trees in the parser tests, will be two children, function arguments and function statements. So if we can find it in the hash map, then we continue on to this bit. If we can't, it's an undefined function. So we get the parameters from the hash map, and we get the past parameters that were given to us in the function call, and we check them against each other. Pushing a new stack frame when we're entering the function, we define here each parameter as a variable in the current stack frame. Like in this one, add a, b, and then we're bringing in these variables, or just numbers 6 and 7. We're there's hidden code here in the interpreter that says let a equal 6, let b equal 7. That's effectively how I'm doing it, by executing a new variable defined statement. And we already defined the function statements before that. So when we're done defining the variables, we can immediately execute the function statements as well. And an interesting uh, thing here is that a function is not executed or checked for anything when it's defined. This is probably not optimal, and a real world situation, we would probably have an optimizer, like with just-in-time compilation. If we wanted to make this a little more just-in-timey, we could take a function when it's first defined and optimize it, and then put that into the hash table instead of just the code that's given. So that's pretty much the function call. And note all these, we're defining a lot of our variables by this syntax, creating a node with children as the given variable. So it's going to be either a node with children as the given variable, which was passed from the parser, or we are returning an error. And in most cases, it is not possible or likely that the code will ever get here. It's borderline unimplemented, but I left in these detailed error messages during debugging. So a function return will just execute the variable that is given. So will an expression. These are all predefined. And this is for undefined node types, which we don't need to worry about because all the node types are in the arms of the match statement. So let's just do that. Now let's look at the tests. So I had 10 custom tests, with the first 4 focusing on math problems. So making this happen was enough of a challenge. That was what required me to do the math expression PEMDAS stuff. This makes sure PEMDAS is working and a multiplication comes before an addition. This, or I guess that's not math focused. This makes sure a return statement returns before the last statement. So this is a 3 because it's just y. We return before this unreachable code happens by design. And this would also happen inside a function. We can have multiple addition operators in a row without parentheses. And PEMDAS also includes exponents. Now the next 3 related to functions. We can have a function with no arguments. We can have a function with 1 argument, and that function can go in a math expression. And we can have this working add function. And the last 3 custom tests are testing that we get specifically defined errors. So wrong number of arguments to a function call, too few and too many give us the same error message. And 2 interesting things going on in this test. We've got an undefined function, obviously, this subtract function that doesn't exist because this is add. And also, we've got wrong, weird syntax. It parses, it gets to the parser, but it wouldn't compile. No, it would compile, but it wouldn't run. Or we're not even compiling. It would get through the parser, but it wouldn't work at runtime. So returning this variable that doesn't exist, but that is not evaluated at all because the add function isn't called, and items within a function only exist or only evaluated when the function is called. So this takes precedence. I could have certainly extended this by having a more robust stack frame system. Only being able to see the last frame makes it so these functions couldn't access items from outside the function that were defined earlier in the program. Any extension to this, I think, would require as well an extension to the parser. Like if I wanted to have lists or arrays, that would have to be parser first, and then only then come through the interpreter. I think the most realistic extension to this would be loops, or conditionals, like a for loop, an if statement. There is no token for that stuff in the lexer or in the parser, but it would be pretty trivial to just add it around this area of the parser, of the lexer, and then just have a if statement, loop, expression statement in the parser, and then bring that through the interpreter. It would be relatively uncomplicated to just use the Rust native loops and stuff for that. Ignore how many tabs I have open. So let me just run cargo test. So as you can see, all these tests work. You can see them running. The output is just all successes. The lexer these are the interpreter tests. The interpreter tests work. The lexer and parser tests work. So that means that all of these are really being evaluated and found to equal their targets. So I think that's it. I'm glad to answer any questions over email. Thank you very much.